Okay, we're going to go ahead and get started. So welcome everybody to the GBO Community Zoom. We appreciate you guys joining us. Just a quick update on the observatory. We have the Green Bank Single Dish Summer School is coming up this summer, June 23rd to 29th. The applications close basically this week, the end of this week. So you can go to the webpage and see the link and click on it and go ahead and register. This is aimed at graduate students, so at that level. So please pass it on to graduate students who you think might be interested. We're going to have a public eclipse viewing party at the observatory April 8th. It's not in the path of totality, where we see a total eclipse. It's off, we're east of that, but we will host a public event. And last time we did this, I guess it was 2017, there was a couple thousand people that came by the observatory. Summer maintenance plans, except for a few weeks of observing in the summer, will be mostly shut down for infrastructure work from May 6th to September 26th. So a limited amount of observing during that period where we take care of some needed infrastructure. So I'm going to go ahead and hand it over to Jay, and he can introduce our speaker.
Thanks very much, Dave. Our speaker today is Jialu Li from the University of Maryland, and she'll be talking about observations of dense gas in the galaxy IC342. Let me remind everyone that this presentation is being recorded for later viewing, and you can get to it through a link on our website. And if you have questions, please submit them through the Q&A button at the bottom of your screen, and we'll get to them at the end of the presentation. Okay, take it away, Jialu.
Okay, thank you very much, Jay, and let me share my screen. Okay, how's it going now?
Looks good.
Okay, great. Okay, thank you, Jay, for the introduction and also the invitation, and welcome everyone for being here today. So today I'm going to introduce some of our recent work with Argus on a nearby galaxy IC342. This paper has been accepted by FJ and is in press now. So I'd like to start introduction of IC342 with the DEGAS survey because this is a very big GBT project with about 500 hours. So basically the DEGAS survey is the Dense Extragalactic GBT+Argus Survey, which is a current one, kind of one of the multiple ongoing survey of dense molecular gas on nearby galaxies. So there are also ALMA and NOEMA or Iran are conducting this kind of project. So basically the idea is to map a couple of density tracers in nearby galaxies and try to observe them in a simultaneous way, and also to map rather big regions among these galaxies. And IC342 is one of the nearest and brightest galaxy in DEGA, and since it was observed at the very beginning time when the Argus was deployed on the GBT, so we also proposed a DTT time to try to observe the first 12CO map of an external galaxy with Argus at the time to test Argus ability for this kind of mapping. So, well, I believe that Argus is possibly known to a lot of people here. I would still like to introduce a few things about it and to emphasize why it's great and why it's powerful to do such kind of job in specifically resolving those molecular clouds even in the external galaxies. So basically, Argus works at 3 millimeters. This is a region where a lot of rich molecular lines are located at. So that's why people would love to use those lines to trace molecular gas. And also because it's deployed on our GBT, which has a 100-meter size. So it would provide a very small beam size from about 6 to 8 arc seconds at this kind of 3 millimeter wavelengths. And also Argus has 16 beams. So it allows a very efficient absorption time, since we just have much more beams taking the signals at the same time. And also because it has the MMC, monolithic microwave integrated circuit technology, so it provides very good sensitivity. So in all, Argus at the GBT is ideal for observations with a large spatial dynamic range. So it allows us to really resolve molecular clouds, especially from external galaxies, very nicely. So in this page, I would like to show you a comparison of what Argus can do, and also some of other very advanced instrument can do. So on the left, I'm showing here a very beautiful NOEMA and IRAM CO map that's taken for IC342. And on the right, we can see that, okay, for this kind of 3 arc minutes times 5 arc minutes region, we have our GBT+Argus map on the right. And so, of course, I admit that this NOEMA map is very beautiful, but I would like to also emphasize the time difference in here. So for the NOEMA and IRAM map, it requires 120 hours of NOEMA and also 43 hours of IRAM. And as a comparison, for the central region of IC342, for this CO map we have taken, we only have used 10 hours, and specifically for ours are the overhead time. So this is what we can do with 6 hours on source. So I hope this is a page with some kind of good advertisement about how Argus can sufficiently map these kind of external galaxies, those molecular clouds there. Okay. And other than the 12CO map that we obtained from the DDT time, I would also like to show you some of these maps that we got for IC342 from the DEGAS survey. So basically on this page, I have on the left panel the Hubble map of the central region of IC342. So basically you can see a very bright starburst inside, and also some kind of S-shape dust that's kind of aligned in a very long path. And in all of these other 5 molecular maps we have in here, they are all moment 0 maps, and I have listed 12CO, 13CO, C18O, HCN, and HCO plus here. And to emphasize one of the things in here is that the 13CO and C18O are observed simultaneously, and so does for HCN and HCO plus. So we really had a very good handle about to avoid some artificial effect due to the instruments. Okay, so we have very nice, beautiful integrated map in here, and we start to ask questions. So the first thing, it seems to be a stupid question, but actually it's important, which is how can we interpret the brightness of the lines properly? We would like to specifically emphasize this question later on, is because we do realize that, okay, we should pay some attention to the excitation condition, also the optical depth condition in here. And the second question is that, okay, so I've been emphasized that the DEGAS survey, it's powerful because it resolved those dense molecular tracers. And as a comparison, in the past, these kind of observations have been usually done with only single beam observations, so only one data point on a bright galactic center. And so now, since we have resolved maps, how does our interpretation reconcile with those based on, those single beam observations at the time? Okay, so first question, let me emphasize our motivation again. So in here, I'm presenting the HCN and HCO plus map, and which are observed simultaneously. And so first of all, we notice that, okay, basically the 2 bar regions, they have almost the same shape, just from a perspective of morphology. And if we plot all of the dots into a scatter plot on the right, we see that, okay, they're indeed very similar and with a very small scatter, and also there's a very constant ratio about HCO plus to HCN. This intensity ratio actually is surprising, not only because it's larger than 1, but because Y is larger than 1. So we know that HCO plus has a larger dipole moment compared to HCN. So this means that under the same kind of temperature condition, HCO plus tends to get excited more easily than HCN, which means that we expect to see HCO plus to be brighter than HCN, which is not the case in here. In here, we see that the HCN is brighter than HCO plus across the whole 1 kiloparsec bar. And so that's why we would like to see, okay, how this could happen. And the way, and the way that we would like to interpret the specific brightness that we see for the line is quite simple, actually, from the perspective that, okay, the line is excited to some kind of temperature, and also how the optical depths kind of attune the brightness that we see. And for this excitation temperature, as I've mentioned before, it really relates it's related to the properties of the molecule, and so that's why we expect to see that, okay, HCO plus tends to be excited more easily than HCN. And as for the facts of the optical depths, basically that's a very simple item. That's 1 minus e to the minus tau that we're familiar about. And so to summarize or to derive what we would see, or the ratio we would see, we would like basically to build some models and to say, okay, under what kind of physical conditions, what kind of excitation temperature and optical depths we can get for some molecule. And then we can try to see, okay, do we get the ratio of 1.2? So basically that's what I'm going to show in the next page. So we take advantage of the tool RADEX to do the modeling. To basically, we input some combinations of the column density or volume density, and to see, okay, how those HCN and HCO molecules would get excited and what kind of ratio they would have. So I have this figure on the left, basically has its x-axis showing the volume density and the y-axis showing the column density of HCN. And for all of the regions in this panel, basically for all of this, each point, they would give you the 1.2 ratio we would like to have. So for all of these contours here, they also related to the abundance ratio of HCN to HCO plus. And so you just randomly select the point in this panel and you read the combination of parameters, you will get the 1.2 ratio. Okay, other than the gray region on the top right. So basically, this figure tells us what are the permitted combination of parameters that can give us this 1.2 ratio. So we can see that, okay, actually we have a lot of choice and we can kind of group them into 1, 2, 3, 4, 4 regions. And but our question is that, okay, even if those parameters, technically, they can give us the ratio of 1.2, but are these regions feasible? So for these 1, 2, 3, 4 regions, I have kind of grouped them, list them on the right. And so you can see a combination of the optical depths and excitation condition they correspond to. So we see that they really correspond to a wide range of excitation condition and optical depths. And so we need to do the work of, okay, try to cut each of them one by one and to see, okay, what's the final one remained. So basically, first of all, it's very easy to rule out region 3 because we can see that for a couple of different conditions, but it really corresponds to almost constant optical depths in here. So we think, okay, this is not possible. And so also for the region of for region 4, because we see that it has almost horizontal parallel contour parallel to the x-axis. So 3 and 4, they really ask for very restrict conditions of optical depths, and we rule them out. And for 1 and 2, they're located very different size. As we can see, the region 1 corresponds to first very large optical depths, and then kind of subthermal excited line condition for both HCN and HCO plus. And 2 is kind of on the contrary, that it asks for rather intermediate optical depths, but a thermalized condition. So while both of them seem to be permitted, we really need to emphasize that based on our observation, region 1 is unlikely because region 1 asks for subthermal excitation. And this is actually very sensitive condition, especially considering that we're talking about a really 1 kiloparsec bar. This is impossible to be kept. So I'd like to summarize what we learned from our discussion previously. So basically is that we can get the permitted region, but also we would like to specifically rule out region 1. And the reason that I would like to emphasize region 1 is because in the past, when people were doing single beam observations, specifically in those galactic centers, region 1 is actually the most commonly interpreted one, specifically based on, for example, when people at the time, they not only have one data point for the 1 to 0 observations of a galaxy, they can also have, for example, 4 to 3, and they calculate the ratio, and they say, okay, 1 to 0 must be subthermal excited, and there's large optical depths. That is a solution. Okay, we will go for it. That's it. And so now we come to the question about, okay, even if people got that region 1 as a solution at the time, is that the only possible solution? Because as I've shown previously before, based on our kind of new Argus observation, when we have this kind of new perspective of this spatially resolved ratio, which is a constant across the galaxy bar, region 2 is our preferred one. So, okay, is region 1 the only possible one solution? And secondly, can we expand our kind of analysis to other galaxies? So I'd like to give very quick answers to the two questions. So the first one is that region 1 is not the only possible solutions, even at the time for single beam observation. So a simple way to kind of replicate this kind of analysis is that, okay, we know we have very nicely resolved Argus map of HCN, HCO+, so we can convolve it. Just to imagine, we have one single beam in the center of IC42. And also there's HCN-423 from GSMT. And we can do this kind of calculation and kind of do what people had done, try to mimic the process and look for the corresponding parameter space. And so on the right, sorry again, this looked to be a crowded figure, but the basic idea is that for this combination of temperature and volume density, and as for these contours also represent the ratio of 1:0 over 4:3. So basically, if we focus on this red region firstly, this is what we were looking for. So we were looking for the region from 3 to 10, and that is corresponds to our IC342 result. And we can read the x-axis from it, and we can see, okay, indeed, this is the region 1 because it kind of has the volume densities region correspond to what we learned in those previous figure. But however, is this region 1 the only kind of possible solution? The answer is no, because we can kind of manipulate this kind of modeling process. And for example, if we decrease our column density by 10 times, we can shift this group of contours to the right, and we will read region 2 as another sample of 3 to 10 in here. So sorry that 3 to 10 is not marked in this figure, but that's represented by this orange color, and that corresponds to region 2. So our answer is that, okay, even if region 1 is one of the explanation, but it's not the only one. And as for the second question about whether our analysis works for other galaxies, because in those single beam observations, people have observed this kind of ratio from 0.8 to 2 already. And so we can indeed try to make those figures via RADX about, okay, can we get HCN-to-HCO+ ratio in this region? And the answer is yes. So first of all, for the figure on the left, even if it looks like another very crowded one, but the basic idea is that, okay, any point on this figure works. You can pick whatever one here. This is because, as I've mentioned before, it's very easy for HCO+ to just be brighter than HCN, so that's why it's very normal to have it this ratio smaller than 1. So any points on the left panel works. And then secondly, it's about the ratio of, for example, 1.4 or 2. So we can see that the pattern looks similar to the one we derived for 1.2. It's only really about a shifting of those permitted regions. So the answer in here is that, okay, region 2 is still a good solution that we would like to get. And of course, actually, we have a lot of other criteria that we've used when distinguish region 1 or region 2 by a lot of constraints. You're welcome to ask about this later on. But basically, the conclusion is that, okay, yes, our method works, and we can expand this to other galaxies. Okay, so now here we comes to the summary page. So basically, I've introduced that we really require instruments that help us with large dynamical range in a figure, which can help us to understand really to get a better idea about distribution of molecular clouds, and then to answer some more important questions. And also Argus is very important in here because it's really efficient in specifically taking large maps. And also we find these kind of constant ratio of HCN to HCO plus, which is larger than 1 across the bar. And the reason that we think is important is because it's this kind of spatially resolved large ratio. I mean, we see that it's really it's constant across the 1 kiloparsec bar. This really kind of provides us a new perspective in thinking about, okay, what are allowed and what are not. So indeed, it's a story more of what is not rather than what is. But we think that in our process of ruling out and cutting off those impossibilities, we can get some idea of, okay, what should be there. And in the end is that we can kind of use these kind of conclusions to compare with what people learned from single dish observations, and also try to expand that into other galaxies that single beam observations have done. So, okay, thank you very much, and I hope this talk brings you some interesting ideas.
Thank you very much for a most interesting talk. Let me remind everyone to submit questions through the Q&A button on the bottom. But I have a question to start with, because you're showing all of these temperature versus density plots, and different places in those plots correspond to pressures that vary by many orders of magnitude. And is that some consideration that you would take in? And also, would you expect the pressure to vary in some systematic way across the bar?
First of all, I would like to make sure, is this the figure that we're talking about, or those previous?
That's fine. That's a fine figure. Any one of those, really. No, not this one, but the one that with the temperature,
yes,
kinetic temperature versus density. Yes, that one.
Yes. So first of all, I'd like to stress that the previous figures that doesn't include temperatures, because we have actually done our experiments with different temperatures, and we found that, okay, it's not very sensitive to the selection of that, and so we selected a representative temperature of 30 Kelvin there. And as for this question, so I think this question also kind of gives me this information that our selection of parameters are not very sensitive to the y-axis, as you can see in here. So that's why we're only reading the changes from the x-axis. And as for the questions about how the pressure influence this, and I would like to ask whether our consideration of the volume density and column density in here already reflects that things.
Yes. Okay. Actually, in that figure, you can see that the pressure for your permitted regions is not varying that much with temperature, but is quite different between region 1 and region 2.
Correct. Yeah, I think, yeah, I mean, combining this y-axis and x-axis, I think the P is kind of fixed, considering. Yeah.
Okay, we have another question. Would you expect different conditions between observations with, say, dwarf galaxies, such as the Magellanic Clouds, versus large spiral or elliptical galaxies?
So if you don't mind, could you the person who asked question provide more conditions about, for example, what to expect about specifically the line ratio in here for dwarf galaxies? Or
let's see, that was just a fixed question. I don't know how to elaborate on it.
Yes, yeah.
I could allow the questioner to speak.
Yeah, would you like to do that?
Absolutely. What was that?
Sure.
AC, I believe
Yes.
it was. Okay, AC, you have the floor. You'll need to unmute. If they are there.
Nope. Okay, well, I don't think we were able to follow up and expand that question at the present time.
Okay.
But let me just add whether in light of that question, you have any general comments. Now, you're actually looking at a sample of galaxies in these spectral lines with Argus. Isn't that correct?
Specifically those well, I mean, I am specifically looking at one galaxy among the sample of galaxies, and IC342 itself, it's a starburst galaxy.
Okay.
We do have an elaboration on that question.
Yes, and the elaboration is, well, I actually don't understand it because the elaboration is between 1 and 2 regions. I guess the question is whether, as a function of morphological type of galaxies, you might expect to get different answers for the same range of parameters.
So what I know, so for example, for the ratio range of 0.8 to 2, so that kind of value is averaged based on, so for those galaxies that only has one data point from the galaxy. So I can kind of imagine that when that galaxy is spatially resolved, so certainly the actual ratio of HCN-to-HCO plus can be much larger than that. But I think the real difference is really about whether this ratio is smaller than 1 or larger than 1. So for example, for these panels that I've shown in here, the representative results would be smaller than 1. Okay, every data point is possible. And on the right, you can see that really this pattern just shifts above or to below if you get a really very high ratio of HCN-to-HCO plus. So regarding of those specific points at a specific, specific location in a resolved galaxy, so I believe you can still apply these figures to think about, okay, what should be the excitation condition and optical depth condition there. Does it make sense?
Yes, yes, it does. Well, we don't have any more open questions right now. And let me just say that it's really good to start seeing some Argus results out and making a difference in our understanding of the interstellar medium in these galaxies.
Yes.
Let me remind everyone that this presentation has been recorded and will be available for viewing within a day or so. You can get it through the link on our website, the GBO website. Please join us in 2 weeks for the next in this presentation, also Argus results. Rachel Friesen from the University of Toronto will be speaking on dynamics in star-forming cores with Argus on the GBT. We look forward to seeing you then. Thanks and goodbye.